It began quietly in late August of 1859. A British astronomer named Richard Carrington stared through his telescope at what looked like two bursts of white fire boiling on the surface of the sun. He sketched them down, marking their place, just before a blinding flash forced him to turn away. 40 hours later, the world experienced something it had never seen before. A curtain of light stretched across the planet. Auroras glowed blood red over Cuba, bright green over the Caribbean. People in New England read newspapers at midnight without a single lamp. To miners in Colorado, it looked as if the dawn had come 12 hours early. Then came the shock. Telegraph operators, 19th century guardians of the world's first information network, noticed their equipment acting strange. Sparks flew from keys. Some telegraph lines carried current without any power source. Operators were shocked by their own instruments. Message papers caught fire. In some places, they unplugged their batteries entirely, yet messages still carried thousands of kilometers through empty wires by the sheer energy flooding Earth's magnetic field. That was the Carrington event, the most powerful solar storm ever recorded. And it didn't just paint the sky, it rewrote how humanity understood the sun. Here's what happened. When Carrington saw that bright flash, he'd witnessed an enormous solar flare, an explosion of charged particles and radiation surging outward at millions of kilometers per hour. Traveling with it was a coronal mass ejection, or CME, a massive bubble of magnetized plasma the size of billions of tons. When it hit Earth, the planet's magnetic field buckled. Geomagnetic currents pulsed through power lines and telegraph wires like shockwaves in steel. The entire planet became an antenna, receiving energy from the sun. In 1859, with only a few telegraph systems in existence, it was mostly an inconvenience and a strange scientific curiosity. But if the same storm hit today, the result would be catastrophic. Modern power grids are infinitely more connected and infinitely more fragile. Each transformer designed to feed electricity to cities depends on stable magnetic balance. A blast strong enough to twist Earth's magnetic field could induce electrical currents thousands of times stronger than they were built to handle. They'd melt from within in seconds. As astronaut physicist Dr. Ellen Stokes from NASA once put it, the sun sneezes and the Earth catches the flu. Our entire digital civilization lives inside that sneeze. That's not poetry, it's physics. When a CME hits, it adds or subtracts magnetic pressure from the planet's field. The planet fights to rebalance, and that motion drives electric currents through anything conductive beneath. Power lines act as perfect highways for that chaos. In 1859, there was no GPS, no aviation, no global internet backbone stretching beneath oceans. Telegraph offices could unplug and wait. Humanity today doesn't have that luxury. Every system, from satellites guiding airplanes to finance networks timing trades, depends on pulsed electricity synchronized to milliseconds. Disrupt that rhythm and everything stops. To understand why, think of the sun as an engine made of plasma, boiling hydrogen gas under magnetic tension. Unlike a simple fire, it has structure. Magnetic fields loop and twist until they snap, releasing tremendous bursts of energy. These aren't random. They follow cycles about 11 years long, like clockwork generated by the sun's own heartbeat. Every cycle peaks in violence, when sunspots darken the surface like burn marks in a processor. During the 1859 event, Carrington didn't know any of this. To scientists of the time, it was an anomaly, one star's outburst, quickly forgotten as the wires cooled and normal messages resumed. But our perspective has changed. We now understand that the Carrington event wasn't an accident in history. It was the first line in a repeating pattern, a warning written across the sky. In more recent decades, we've seen smaller echoes. The 1921 railway storm-setting telegraph offices ablaze in New York. The 1989 Quebec blackout plunging 6 million people into darkness when a lesser CME collapsed the Hydro-Quebec grid. Those were tremors compared to the blast Carrington recorded. Scientists estimate that if the same strength of storm struck Earth today, the damage to transformers alone could take years to repair. During that time, continental grids would remain dark, satellites would wander from orbit, airplanes would lose navigation, communication would reduce to analog radio at best. The cost? Potentially trillions of dollars, an economic impact greater than any war in modern history. And it all started with a flicker on the surface of a star, no further away than 8 light minutes. For Carrington, it was simply a day interrupted, a bright flash in his eyepiece, recorded, dated, put away in a notebook. But buried in that notebook was proof that technology and astronomy were about to collide forever. The telegraph proved our inventions could stretch across continents. The Carrington event proved that the sun could erase them in a single heartbeat. To grasp the magnitude of that connection, to see why our modern world lives at the mercy of something 93 million miles away, we need to go deeper into how the sun itself behaves. Because behind those storms and flares lies a code, one we're only beginning to read. The sun's own logic of magnetism, flow, and feedback, its software of light and fire. And as we'll learn, that code can crash. The sun's code. Get this, the sun isn't a static ball of fire. It's more like a living machine made of plasma and magnetism, constantly rewriting itself. Think of it as a loop of software running across a 4 million kilometer sphere, with currents for code and magnetic fields for logic gates. Each time those magnetic fields twist, tangle, or flip, they can spark an event powerful enough to reach across space and touch us here on Earth. Every 11 years or so, this star completes what scientists call the solar cycle. During that period, the sun's magnetic poles slowly weaken, crumble, and flip in a process that would look like chaos if we could watch it unfold up close. It's not day-to-day predictable. There's no neat on and off. Instead, it's an algorithm of turbulence. Hotter plasma rises, cooler plasma sinks, and in that motion, electric currents generate complex magnetic patterns. Those patterns aren't random. They evolve, interfere then. When tension becomes too much, break. That's when a flare or a coronal mass ejection bursts outward. Some scientists have begun calling these moments magnetic reconnection events, but others have started borrowing language from software engineering, calling them code faults. Because the sun really does behave like a self-modifying system. It loops through instructions written in magnetism and plasma flow. Dr. Carla Ramos, a solar physicist from the European Space Agency, once described it this way. Each cycle is the sun debugging itself, but sometimes the patch fails, and when it does, we get a flare that erases half the code. She wasn't joking. Every magnetic inversion rewrites massive regions of the solar surface. When loops rupture near the surface, they release enough energy to power the entire human civilization for hundreds of thousands of years, all in a matter of minutes. We're living right now at the crest of one of those cycles, Solar Cycle 25. It began quietly in late 2019, and scientists project its peak around mid-2025. Over the past 2 years, the sun's face has been peppered with growing clusters of sunspots. Each one is a trap of tangled magnetism, storing vast electrical energy like a capacitor waiting to discharge. In February 2024, the largest sunspot group in decades stretched across nearly 1/5 of the sun's visible disk. To solar scientists, that's like staring at a fault line ready to rupture. These dark spots might look passive, but think of them as stress points in a loop of code that's just reached its breaking condition. Observatories like NASA's Solar Dynamics Observatory, the SDO, watch them day and night, imaging the sun in wavelengths of light we can't see. Ultraviolet, extreme ultraviolet, X-ray. Each wavelength traces a different layer of solar activity, revealing the architecture of that magnetic code. When you look at time-lapse imagery from the SDO, it's mesmerizing. The surface bubbling like boiling metal, flares twisting upward in arcs taller than the Earth itself. You can see the flow of information across the plasma. And the strange thing is, it almost behaves with purpose. That's partly why some researchers at NASA and ESA started using the software metaphor seriously. The sun learns. It remembers magnetic configurations and repeats them in similar patterns over consecutive cycles, as if rewriting subroutines with better efficiency. Meanwhile, deep inside, convection currents churn millions of kilometers down. Magnetic fields are dragged and stretched around each other like tangled cables inside a computer control board. Every stretch amplifies field strength. Every twist stores more potential energy. Eventually, somewhere near the surface, something snaps, and all that energy is ejected outward as a flare. We can trace this architecture through what scientists call butterfly diagrams, showing where sunspots appear across the solar surface during each cycle. Early in the cycle, they appear near the poles. Later, they migrate toward the equator. If you stack a century of these diagrams, it looks remarkably like an evolving neural net, each cycle training new magnetic pathways, pruning others. It's surreal, almost as if we're looking at the thought patterns of a star. Now here's where it gets urgent. The closer we get to 2025, the more erratic this data becomes. Satellite readings of solar wind, streams of charged particles flowing from the sun, show greater fluctuations than during the previous cycle peak in 2014. According to data from NASA's Heliophysics division, the average speed of high-intensity solar wind bursts has increased by roughly 20%. That might not sound like much, but in space weather terms, it's the difference between a spark and a blowtorch. The more distorted the sun's magnetic field gets, the higher the chance that a violent flare will coincide with a direct Earth-facing ejection. When that happens, we don't get much time to react. Depending on the event's speed, the resulting plasma could reach Earth in as little as 12 hours. To gauge this behavior, scientists use magnetograms, maps of the sun's magnetic field lines, color-coded by polarity. On those maps, you can literally watch energy gathering like storm clouds. When opposite polarities collide, it's a ticking clock. If the loops reconnect smoothly, energy disperses quietly. If not, the system explodes, a coronal mass ejection on a collision course with everything powered by electricity. Dr. Ishan Mehta from NASA's Goddard Space Flight Center summarized the problem bluntly during a 2025 update. The sun isn't malfunctioning. It's operating exactly as designed. The problem is that we built our civilization inside that operating system without understanding the bugs. That statement stuck in the scientific community because it reframed the whole concept of solar weather. It's not a seasonal inconvenience. It's a fundamental part of the environment Earth evolved under but technology ignored. Think about that. The same star that gives us life also writes the rules for our technology's survival. Satellites, grids, navigation, all depend on electromagnetic stability that can vanish with a single update. The sun never sends us advance notice about. Across observatories worldwide, teams study these cycles like meteorologists tracking hurricanes, except our hurricane is 93 million miles away and larger than the solar system's ability to protect itself. The Solar Orbiter mission, orbiting closer to the sun than Mercury, now captures the first close-up data of magnetic twists lifting off into space. What scientists find consistent in every eruption is pattern recursion, the same sequence of magnetic buildup and release, varying only in intensity. It's repetition with escalating potential, like a software loop heading toward overload. And at the peak of the current cycle, we're seeing record-breaking flare frequency. In May 2024 alone, more than 20 powerful M-class flares and several X-class flares, the strongest category, were recorded. When sunlight reaches us 8 minutes later, it looks beautiful. But those flares also launch radiation storms that hammer satellites, distort GPS, and ripple through high-altitude flight paths. Each of those blasts is the sun's debugging process at work, rewriting and rebooting as it manages its own internal logic. But for us, they're warnings. Every increase in activity reminds scientists that a Carrington-level event isn't rare, it's overdue. Statistically, odds suggest Earth should face another in the next century. The odds for it happening during an active solar maximum like this one are higher than at any other time in a decade. The universe hides its danger behind familiar beauty. We look at the sunrise and see peace, not computation. Yet that sphere is ticking, solving magnetic equations that occasionally output catastrophe. The sun's code is immense, ancient, and self-sustaining, indifferent to what orbits around it. Here's the paradox. The sun doesn't mean harm. It simply runs its process, cycle after cycle. It's us who adapted too well to the brief calm between storms. Our circuits, grids, and satellites are written in smaller, more delicate code, all dependent on a system we can't control. And that's why scientists now see the sun less as a ball of gas and more as a processor, a cosmic operating system tuned for chaos management. Its runtime never ends. Its errors, when they happen, are measured in auroras and blackouts. So as we watch the magnetic fields tighten once more, the question shifts from curiosity to survival. What if the next glitch in the sun's code doesn't just brighten our night skies, but crashes our entire civilization's operating system? In every observatory window glowing with real-time solar data, that's the line we're waiting to see cross the screen. AI discovers the sun's patterns. For more than a century, solar forecasting was a matter of observation and luck. Scientists tracked sunspots by hand, logged flare frequencies, and waited. But now, machines have joined the watch. In 2025, a new generation of models turned the sun's chaos into data and then into prediction. It started with one ambitious project, NASA and IBM's Surya model, a deep learning system trained on the heartbeat of our star itself. Surya consumes more information about the sun in a day than a human scientist could analyze in a lifetime. 14 years of solar dynamics observatory data, millions of images taken every 12 seconds, feed its neural network. That imagery spans ultraviolet, magnetic, and visible light, mapping not just brightness but behavior. What emerged wasn't just a pattern, it was a language. Surya began to recognize the precursors of flares, the subtle darkening around sunspot clusters, the tension in magnetic loops twisting before release. Dr. Ravi Patel, part of the NASA-IBM collaboration, described it simply. We taught the model to see stress in the sun the way a doctor sees a pulse under skin. That vision granted something humanity never had before: time. 2 hours of it, to be exact. Surya can forecast major solar flares up to 2 hours in advance, doubling our previous warning window. It pinpointed events that, to the naked eye, looked harmless until 15 minutes before eruption. That lead time can mean the difference between a scrambled satellite and one safely powered down. Meanwhile, halfway across the world, researchers at NYU Abu Dhabi pursued a different angle, predicting not flares but the aftershocks, solar wind. Their AI model, trained on decades of solar wind speed data and extreme ultraviolet imagery, now forecasts those speeds 4 days out with 45% more accuracy than operational models before it. That means we can anticipate when charged particles will buffet Earth's magnetic field, shifting currents and auroras. For space weather centers, this was revolutionary. For the first time, we could see the storm before it hit. But as every scientist involved quietly admits, foresight doesn't equal control. 2 hours, 4 days, it's warning without shelter. The challenge isn't the signal, it's the civilization listening on the other end. In May 2024, both Surya and NASA's Dagger model, a real-time geomagnetic forecast system, were put to the test. Midway through the month, a sequence of X-class flares erupted, leading to one of the strongest radiation storms in 20 years. Older models flagged uncertainty. Surya identified a high-risk signature 2 hours before the first eruption. Dagger's downstream prediction signaled geomagnetic disturbance with a 30-minute lead, updating every minute thereafter. When the plasma reached Earth, communications wavered, radio faded, satellites switched to safe mode, and yet damage was limited. Operators had time to act. For scientists, that was proof of concept. AI could read the sun's pulse faster than nature could strike. But even success carries weight. The reality is, those warnings buy us minutes, not immunity. We can't turn off Earth's transformers the way we can park a satellite, said Dr. Layla Mahmood, a heliophysicist at Goddard. Our grids are always live. That's the problem. While Surya studies the sun, AI back on Earth runs simulations of what would happen if a Carrington-Scale flare targeted us now. The models paint a grim picture. Global transformer collapse within 90 seconds, chain reactions crippling intercontinental links, communications lost as GPS satellites fry in orbit. The projections show cascading blackout zones spreading across the continental United States within half an hour, then Europe, then Asia as grid interconnectors fail in sympathy. Billions in seconds. And still, researchers push the algorithm further. Each new data faint from the Solar Orbiter or Parker Solar Probe becomes another line in Surya's dataset, a finer texture in the sun's unpredictable code. The model doesn't just predict flares, it visualizes them, producing animated outputs of magnetic loops twisting before ignition. To scientists, it's like watching the equations come alive. To engineers, it's a stopwatch counting down to catastrophe. One subtle discovery changed everything. Training runs showed that before a massive flare, the solar magnetogram pattern develops what AI scientists call entropy drift, a measurable increase in the randomness of magnetic pixel data. It's like the sun's surface gets noisy, disordered, unstable. Surya caught that drift hours before visible flares on multiple occasions. The implication: the sun may advertise its next outburst long before it explodes, if we know what to look for. Dr. Patricia Kwan from the Solar Physics Data Lab shared that insight during a 2025 briefing. For the first time, we're decoding precursors invisible to humans. AI is teaching us to listen where our eyes can't see. The room went silent after she said it, because it marked a shift. We've built machines that can read another star's breathing. We've turned the sun into a data set. Yet for all the triumph in that, the tension lingers. These models expose a cruel truth. Predicting an event of cosmic scale doesn't make us safer from it. The scale of response needed to shield an entire planet is beyond countdowns and dashboards. AI can whisper, "It's coming," but it can't build a better grid, launch instant shields, or harden transformers faster than plasma approaches. It's intelligence chasing inevitability. Still, the work continues. Every cooperating observatory, from NASA's Goddard to NOAA's Space Weather Prediction Center, feeds the system constant updates. Solar physicists watch Surya's predictions overlay with real flares, color coding where it guessed right and where it missed. The accuracy climbs, pattern by pattern. Scientists once joked about wanting a space weather Doppler radar. Now they have something better, a learning machine watching a star. Through the Surya model's open source release in 2025, researchers worldwide can test, improve, and deploy its predictions. It's hosted publicly, its code transparent, encouraging collaboration far beyond NASA. Universities in Japan, India, and Europe are already using it to cross-check wind speed and flare impact forecasts. For once, the sun's menace has united global data, rather than dividing it. But in every dataset lies a warning quiet as static. The better we understand the sun, the clearer we see our vulnerability. Forecast skill improves by 15%, lead time doubles, yet the stakes only grow higher. As solar activity intensifies into its maximum, the Surya team finds itself not celebrating accuracy but racing time. Because behind every red flag the model raises, every flare predicted hours before ignition, lurks a question that no algorithm can answer. What happens the day the biggest alert goes live, and there's nothing left to shut down? From supercomputers crunching heliophysics in Maryland to engineers recalibrating transformer circuits across Europe, Everyone knows what's coming. The sun's patterns are no longer a mystery. They're a timetable. And AI, the first technology able to read that timetable in real time, has become our interpreter of cosmic intent. Still, those glowing predictions on scientists' screens, the ones showing plasma streaming toward us, are not comfort. They are reminders. The sun doesn't plan, it pulses. It plays out its magnetic arithmetic as it always has. We're the ones betting our power, our satellites, our sense of normal life on the hope that this time, the calculation resolves quietly. And when the data scrolls, and Surya's neural net highlights one particular region flaring brighter than the rest, scientists hold their breath, because that glowing signature means something is about to change. 2 hours of warning. 2 hours to prepare for civilization's most fragile dependency to be tested against nature's oldest routine. It's progress, and it's still barely time to blink. The fragile web powering the world. It's easy to imagine a cosmic storm as something distant, somewhere between sci-fi and myth.